This video is going to be the first in a series of videos that I talk about, well, I want to get into conic sections, into the geometric definition and how that relates to its algebraic definition, how we go from a geometric description to an algebraic definition. So we're going to talk a lot about topics in the Cartesian coordinate system, and I guess it'll be kind of an introduction to analytic geometry. So to start off, I want to talk about, well, what are the Cartesian coordinates? I've kind of taken for granted that in my previous videos that this is already knowledge that we have, but I won't take that for granted in this video. Just to try and explain everything from the ground up. There's a lot of detail that goes into this that I might not be able to cover all of that detail, and so there might be stuff that I don't explicitly say in this video or in the next several videos, but I might get around to making this series a lot better, hopefully. But I'll just start off. This is a Cartesian coordinate system. So this is constructed with a horizontal axis, the x-axis, and a vertical axis, the y-axis. These axes are perpendicular to each other, and we can pick points on this plane. So I can just pick a point over here, P1, and I'll let that just have some value, x1, y1. And what that means is that this has a displacement of x1 units horizontally and a displacement of y1 units vertically. So those are the two ingredients of a point are going to be so this is also called an ordered pair, a horizontal displacement and a vertical displacement. So the next maybe most basic structure in a two-dimensional plane would be a line, and I've already gone over lines a little bit, but a line's most basic form is going to be ax plus bx. Plus by. Ax plus by is equal to c. So this is a linear relationship, and it constructs a line in a two-dimensional plane of x and y values. We have also seen lines written as y is equal to mx plus b. This is a convenient form because it gives us a slope and a y-intercept. And also that lines can be written as y minus y naught is equal to x minus x naught. Y minus y naught is equal to m times x minus x naught. M is once again the slope, and then we have a point x naught y naught in the plane. So I think this is called point slope form, and this is derived from the equation for a slope, y minus y naught divided by x minus x naught. Or you might see y2 minus y1 is equal to x2 minus x1. And then for the equation of a line, we let one of those sets of points be variable, and then this is our known point. So we can construct a line given a point and a slope. And that makes sense. I could take a point on here, and then I say, well, I want a slope of 1. Well, I could just, then I construct the line that way. Or if I wanted a slope of 2, it would look something like that. And then so on and so forth. So I like this form because it shows us it's derived from the equation of a slope. So if I were given 2 points, if I were given 2 points, x1, y1, and y2, x1, y1, and x2, y2. Let's write those points here and here. So this is point 1 and point 2. And point 1 is x1, y1, and point 2 is x2, y2. So this is, I guess, also a definition. This is a definition of a slope. So the slope between those 2 points is going to be y2 minus y1, or the difference here. So this would be y2, this would be y1, this would be x1, and this would be x2. I know this might be really basic examples for some people, but I don't want to assume that this is given knowledge, so I just want to go over it really quickly. So once again, P1 is x1, y1, or a horizontal displacement of x1, vertical displacement of y1. P2 is a horizontal displacement of x2 and a vertical displacement of y2. These are arbitrary values. Actually, x2 and y2 could be negative, or it could be in any of these four quadrants. But I'm putting them in the positive quadrant just because it makes sense to think about it in that way. Alright, so the slope is y2 minus y1, or this distance here, this vertical displacement between P1 and P2, divided by the horizontal displacement. And so we kind of see what slope measures now. Slope measures the change in y per change in x. So slope will commonly be used to describe rates of change, or it is a rate of change. It's a rate of change of y per x. So we can also see slope, and this is commonly written like this, delta y over delta x, or change in y over change in x. And we can also see how this is related to a line, because a line, we know, has a constant slope everywhere. That's why we can let m be constant here, and then we can take one point and a constant slope, and we can construct a line in that way. I think there's maybe like 2 more points I want to go over here. And that's going to be, given these 2 points, P1 and P2, how can I find the distance between those 2 points? Well, that would be, we could write it like this. What is the distance between P1 and P2? So I guess this is like a function that takes in these 2 points and gives me the distance. So the way that we can find that is we can find this change in y. We can see this as a triangle, and the distance is going to be the hypotenuse of that triangle. So if I can find this length and this length, then I can find that length in terms of those 2 lengths. And so that's going to be represented, well, if this were a triangle, and let's say this is P3, I'll just put in a new point, call it P3, that's going to be x2, y1. Now, I know if this is a triangle, then P1, the line P1, P2 squared, or the hypotenuse of that triangle squared, is equal to each of those sides, the sum of the 2 sides squared, or P1 times P3 squared plus P2 P3 squared. Alright, so now P1, P2, or I'll just leave it as P1, P2 is equal to the square root of, now what's P1, P3? Well, I could just represent that as x2 minus x1, the distance, squared, plus, and P2, P3, I can just represent that as y2 minus y1 squared. Alright, so now I have it in terms of x2, x1, and y2, y1. This is the distance, P1, P2. Or I could write it like this, the distance between P1 and P2. So I know it's, I'll just rewrite it up here, x2 minus x1 plus y2 minus y1. And those are squared. So this follows from the Pythagorean theorem. I don't remember if I said that earlier, but that video is definitely going to come before this video, Pythagorean theorem. And this is how we see it graphically on a Cartesian plane. I think there's one more thing I can say here, and that's going to be if we're talking about midpoints. This is definitely not a proof of this, but if I wanted to find the midpoint here. Now let's erase P3 and let's put it here. We'll call this PM actually. So PM, how can we find that? Well, if we were going to prove it, we'd want to construct these little triangles here, and then we'd want to prove that this triangle on the top is congruent to this triangle, meaning each side is the same, so that P1 PM is the same as, or is congruent to PM P2, the line. And then if those are congruent, then we can prove that PM is the midpoint. And then we can use that result by the results of these congruent triangles to say, well, P1 to, we'll call this XM, and then YM. So I know PM is XM, YM. And, well, how we find that is we found those two triangles are congruent, so so P1 XM is congruent to XM X2. This is maybe a little more detailed, and I'm just kind of giving a brief overview. But the midpoint formula, if I wanted to find the midpoint, or PM, is going to be X2 plus X1, or X1 plus X2, all right, divided by 2, and Y1 plus Y2 divided by 2. And the reason we can do that is because we know the midpoint is going to be the average of two distances. If I take the average, or if I add them up and divide them by 2, that gives me the midpoint. That's another theorem in geometry that I might go back and like retroactively do more detailed proofs of this type, and this I definitely will. I'll go back and I'll do some more detailed proofs, but this is kind of just a quick overview. If we're just talking, if we have x1 and x2, and I want the midpoint between, if I have P1 some point in the Cartesian plane, P2 some other point in the Cartesian plane, I want to find the midpoint of those, and I can use this formula here. And there's more in-depth proofs we can do, but that's kind of more of a subject in geometry, and that might be for a different playlist. But, so let's see. I think this is all we need to start talking about more advanced structures, algebraic structures or geometric structures like circles. I'm going to use this to talk about circles in the next video, I think, and actually ellipses, and this is going to be used to construct algebraically all of the conic sections, which is what this playlist is going to be focused on. Excuse me.